Okay, let's continue. So now let's introduce our next thing, which is the Kkt condition. So let's see what's this. So previously we have introduced Lagrange relaxation. So now we're going to present a very useful optimality condition for general nonlinear programs. Here, this is going to be something similar for the first order condition for unconstrained problems. Now you may consider the Kkt condition as the first order condition for constrained optimization. Okay, so let's see what's this. So it's going to be a little bit more complicated, but let's try to do it slowly. So for a regular nonlinear program, so let's ignore this regular term for a while. For a regular nonlinear program, which has a one objective function, several constraints, and you have n variables m constraints, and let's say this is a maximization problem. Then, if our x bar is a local maximum, then we know there exists lambda, where we have m lambda, one for each constraint. Okay, there exists a lambda vector such that you have three things to happen. First, your x bar is going to satisfy all your original constraints. That should be true, otherwise it cannot be a local maximum. Okay, and also your lambda should be non-negative. So you know the conditions are derived somehow following the ideas of Lagrange multipliers. If you have this, when you do Lagrange relaxation, your lambda should be non-negative, right? So this is somewhat familiar. And also, your lambda and your x bar should satisfy this thing. Okay? The gradient of f at x bar should equal to the sum of all the lambda times the gradient of g at x bar. So this looks a little bit weird, but later we will show you what does that mean. And lastly, your lambda and your your b minus g, they should multiply to 0. So this thing is also somewhat familiar. This is the complementary slackness for linear programming, right? In some sense. So you have a constraint, and for a constraint you have slack. Bi minus gi is your slack. Your slack times your primal slack times your dual variable gives 0. That's complementary slackness. So all to all, this in some sense is saying that when you have a primal nonlinear program, if you say your x bar is primal optimal, then there means you may find a set of dual variables such that you satisfy all these things, including the two solutions. They should satisfy your complementary slackness. Okay, so that's pretty much some intuition. Here there are several things to remind you. First, all nonlinear programs in this course and most in the world are regular. So to define regular really requires a lot of efforts. So technically that's called constraint qualifications. And for example, in one situation is that your feasible region should have non-empty interior or something like that. But because these constraints are, these conditions are so easy to be satisfied for practical nonlinear programs, so let's ignore that part to make our life easier. If you are really interested in the definition of regular, you need to look for other advanced courses, but let's stop here. Let's just assume our programs are regular. And also, you may need to see that this is talking about local maximum instead of global maximum, because this is just a nonlinear program. If in general you don't know whether it is linear, you don't know whether it is convex, then this is just guarantee. This is just a condition for local optimum. This condition is necessary for all nonlinear programs. Okay, this is just a necessary condition, just like first order condition. If there is no convexity, then first order condition is just necessary. Okay, but if you have a convex program, if this is convex, if the feasible regions are convex, then this becomes a necessary and sufficient conditions. Okay, so that's about the Kkt condition. So these are just words. Let's get some more insights about the Kkt condition. We may group all these conditions to be satisfied into three groups, okay? Primal feasibility, dual feasibility, and the complementary slackness. So very quickly, let's take a look at each of them. For your X bar to be a local maximum, what you need is that first, you need to have primal feasibility. Your X bar must satisfy all those primal constraints to make it a feasible one. Well, that makes sense. The third one is complementary slackness, as we mentioned. So your dual variables and its associated primal slack, their product should be 0. Okay? So that means if you have a non-binding constraint, which is non-binding at your proposed solution, that corresponding Lagrange multiplier must be 0. Or the other way, if your Lagrange multiplier is positive, that constraint must be binding. Okay, so that's also something you need to satisfy. And the last one, we call it dual feasibility. So dual feasibility, first is your lambda must be non-negative. So the non-negativity of lambda here is of course due to the way we write down our Lagrange relaxation. As we previously mentioned, if max becomes min, if minus becomes plus, if b minus g becomes g minus b, whatever, then you may flip the sign for lambda to make it work. Okay, so your lambda should make sense. Your lambda should be chosen, should have the correct sign to reward feasibility or penalize infeasibility. And then you have the last condition, which is this one. This is actually the first order condition for your Lagrangian. Okay, so let's take a look at this. This part is our Lagrangian, right? Original objective value plus the additional term we add through Lagrange relaxation. So for your Lagrangian, your lambda and your X bar should make its gradient 0. So that's why we say the Kkt condition is the first order condition for constraint optimization. But you don't just differentiate your objective function. Instead, you differentiate your Lagrangian. If a solution can be optimal, can be locally optimal for your original problem, okay? So suppose your original problem looks like this, and this is your feasible region. Suppose you have an interior solution that is optimal, okay? Then in that case, its gradient of f must be 0 because it is it is interior. And also because you know there are boundaries, okay? So that means it's going to make all your lambda 0 because there are some gaps between this solution with those boundaries. So you're going to have positive slacks. Then your lambda would all be 0. So for an interior optimal solution lambda, this equality would be satisfied. Okay, that somehow makes sense. Of course, here we are talking about nonlinear programs. So in general, there may also be boundary solutions. All right. Then for boundary solutions, you're going to get some lambda that is positive instead of 0. Then we're going to require these conditions, these first order conditions, to be satisfied. So we don't have time and efforts to prove the Kkt conditions for you. That may be too much for this course. But we may do have some visualization or some examples to give you some intuitions. That's something we will do.